Welcome to the Explainer. So if you've ever stared at a massive polynomial equation and felt like you were trying to read an alien language, well, you're in the right place. Today, we're not just going to plot tedious point after tedious point. No way. We're going to treat graphing like a true detective investigation. Think of this explainer as your investigator's handbook. We're going to look at an equation like it's a suspect's DNA profile. By the end of this, you'll be looking at a string of algebra and instantly predicting its sweeping curves, its sudden bounces, the whole shebang, all without plotting a single point. Okay, let's take a really quick look at our roadmap. We'll start with the power function foundation, move on to building the polynomial function, then decoding the leading term, finding the hidden zeros, and finally, multiplicity and turning points.
All right, section 1, the power function foundation.
To start our detective story, we really have to meet our most basic single-term suspect, which is the power function. The crucial thing to remember here is that a power function only has one single term. It's basically a marriage between a real number coefficient, which kind of acts as a stretcher or compressor, and a variable raised to a fixed real number exponent. And that exponent, it's the absolute heart of the function. If you change that fixed exponent, you literally change the entire behavior and identity of the graph. It's the core personality of our suspect. Now let's pre-bunk a really common misconception right off the bat, because this trips up so many people. A power function has a variable base and a fixed exponent, like x raised to the third power. Notice the variable is down on the ground level. An exponential function, on the other hand, flips that completely upside down. It has a fixed base and a variable exponent, like 3 raised to the power of x. It's a totally different class of function with entirely different behavior. So definitely lock that difference into your brain right now.
Moving right along to section 2, building the polynomial function. Now, what's really fascinating is what happens when these individual power functions team up. We know polynomials are built by adding or subtracting these power functions, but we gotta ask, does every single power function automatically get to be part of a polynomial? Do they all make the cut?
Well, the short answer is a hard no. Polynomials are incredibly smooth, continuous, well-behaved curves, No sharp corners, no breaks, no weird holes. Because they demand that kind of perfection, they absolutely reject any terms that bring chaos. So that means no negative exponents, no fractional exponents, no variables trapped inside square roots or hiding in denominators, and definitely no variables acting as exponents. Any of these rule breakers? Instantly kicked out of the polynomial club. Let's actually play a really quick game to see if we can spot these rebellious non-polynomials. Looking at this first one, perfectly fine all whole number exponents, so yes, it's a polynomial. But check out that second one. See that fractional exponent of 1/2? That's just a radical in disguise. Denied. The third one has a -3 as an exponent. Also denied. And the last one, the variable is acting as the exponent, making it an exponential function. So no way. Just by checking those exponents, you can instantly spot a true polynomial. Let's jump into section 3, decoding the leading term. So before we do literally anything else with a polynomial equation, we have to track down this leading term. Why? Because this term, the one with the highest degree, is the boss. It completely dominates all the other terms as our x values get massively large or massively small. Sure, the other smaller terms might add some wiggles in the middle, but the leading term's massive growth controls the end behavior of the whole entire graph. It tells us exactly where the graph starts on the far left and where it ends up on the far right. Now, be super careful to avoid this classic trap. Actually, scratch that. Let me emphasize this because it's huge. When you're hunting for that highest degree, if you happen to have a term with multiple variables, say x squared times y to the 5th, you absolutely must add those exponents together to get the degree. 2 plus 5 gives you a degree of 7. Do not multiply them to get 10. It's such a simple addition rule, but forgetting it will completely throw off your entire investigation. Okay, this matrix right here, this is your absolute best friend as a math detective. The leading term test proves that just by checking 2 simple things on that boss term, whether its degree is even or odd, and whether its coefficient is positive or negative, you can predict exactly where the ends of your graph are pointing. If the degree is even, the ends do the same thing. A positive coefficient means both point up to the sky. Negative means both point down. If the degree is odd, they go in opposite directions. It's this elegant little shortcut that gives you this sweeping frame of your graph in like 2 seconds. All right, section 4, finding the hidden zeros. So we know where the graph starts and ends, but what is happening in the middle? That brings us to this dramatic, all-important number, 0. In the graphing world, 0 isn't just nothingness, it's the exact y value we have to hunt down to find where our graph intersects the x-axis. These intersections are like our anchors, the specific spots where the graph touches the ground line. And here is our actionable 3-step checklist to find them. This turns abstract theory into a totally repeatable process for decoding those hidden x-intercepts, which, by the way, you'll also hear called roots, solutions, or zeros. Step 1, we force the entire function to equal 0. Step 2, we factor the polynomial completely down to its core building blocks. And step 3, we use the zero product property to solve for x. Basically, if a bunch of things multiply to equal 0, at least one of them has to actually be 0 itself. Let's quickly clear up another super common mix-up. Finding your zeros, your x-intercepts, means setting the entire function f of x equal to 0. That is totally different from finding the y-intercept. For the y-intercept, you do the exact opposite. You plug 0 in for x. So please don't mix up your clues. Zeros give you the horizontal crossing, the y-intercept gives you the vertical one. Finally, section 5, multiplicity and turning points. To really get the shape right, we need to talk about multiplicity. Multiplicity is just how many times a zero's specific factor shows up in your completely factored polynomial. Visually, it's just the exponent attached to that set of parentheses. But behaviorally, oh, it's huge. It dictates the kinetic energy of the graph right at the exact millisecond it hits the x-axis. This is where it gets really fun. If that multiplicity exponent is an odd number, like 1, the graph just punches right through the axis. If it's a higher odd number, it still punches through, but it kind of flattens out for a split second as it crosses. But, and here's the really cool part, if the multiplicity is an even number, like 2, the graph dramatically touches the x-axis and bounces right back the way it came, exactly like a trampoline. And the higher the even number, the flatter that bounces. So the exponent literally choreographs the graph's physical movement. Now, as we're putting all this together, remember this rule. The degree gives the maximum possible number of real zeros, not the exact number. Think of the degree n as a speed limit. The graph can have at most n real zeros, but because of those even-numbered trampoline bounces we just looked at, or maybe parts of the graph just floating above the axis completely, it might actually have fewer real roots. It's the maximum, not a guarantee. So, between all those bounces and crossings, the graph obviously has to change direction at some point, right? We call these spots turning points. It's exactly what it sounds like, a point where the graph switches from increasing to decreasing, or vice versa. You can think of turning points as the local minimums and maximums. They're the exact spots where you stop climbing and start descending on our little mathematical mountain road. Here is the final clue to our case. If a polynomial has a degree of n, again, that's the highest exponent from our boss leading term, the graph will change directions a maximum of n-1 times. So say you have a degree 5 polynomial, it's going to have at most 4 turning points. It just ties the whole visual shape together so perfectly. All right, you've officially got the tools. You've mastered the building blocks, you've cracked the code on n behaviors, and you know exactly how multiplicities make a graph punch through or bounce. You can absolutely sketch a complex graph just from an equation, but I want to leave you with this final thought to ponder. If you walked into the middle of a case and only had the picture of the graph, do you think you could reverse engineer this entire detective process and write out the exact equation from scratch? Think about it. Thanks for hanging out with me for this explainer, and definitely keep that mathematical curiosity alive.